Right, this is mathematical modelling. We're going to model a lake contamination caused by a chemical spill. To begin with, like all mathematical models, you have to make some assumptions to simplify and, well, basically build a model. So the first assumption is that all the sources of the pollution have been removed, and all pollutants can't degrade or decay, and we have an even dispersion. So it's evenly distributed across the whole of the volume of the lake. Now the flow of water in and out is constant, so we're neglecting things like rain and seasonal changes. Now we ignore water gains, and losses, and we take the volume of the lake to be constant. Now we choose the parameters and the variables. T equals time in seconds, since all the sources of pollution were removed, and M of T is the mass of the pollutant in kilograms in the lake at time T. Now CT is the concentration in kilograms per cubic meter of pollutant at time T. Now our parameters, C target is the target concentration level. It's the level we want to get to, and it's in kilograms per cubic meter in the lake. Now T here is the time it's taken in seconds to reduce the concentration of pollutant to the target level, or given here, C of T equals the target level. Now V is the volume in cubic meters of water in the lake, and R is the water flow rate in cubic meters per second in and out of the lake. Now K equals R over V, which is the proportionate flow rate in seconds. Now we go on to formulate the model. Now as we've already said, water is uniform, and the relationship between concentration and mass is given here, where concentration over time equals mass over time divided by its volume. Now we have an input-output principle, where the input-output principle here, which we'll get to later. Now the accumulation equals the input minus the output. In the interval T and T plus delta T, the volume of water leaving the lake is this, R delta T, which we've already said at the top from our assumptions and definitions, that R is the flow rate through a delta T, delta time. So multiplying by concentration, which is assumed to be uniform, gives the mass of pollutant that leaves the lake in the time interval R C of T delta T, or R over V M of T delta T. Now this is the output. The accumulation of pollutant over T plus delta T is the difference between M T delta T and MT. That is MT plus delta T minus MT. Now we apply the input output here, which is just we're just subtracting one from the other. Now we get this here, where it's 0 because we have nothing coming in, our original output. So it is minus R over V MT delta T, and we replace R over V by K, and now we divide by delta T as delta T goes to 0 to get the derivative here, where, as we already said, K equals R over V. Now that's one differential equation. Now we go about solving this. Now M of T equals M of 0 e to the minus K e to the minus KT, where this is just a basic differential equation, which is, it's a basic solution here, which I'm assuming if you've got to this point, you already know this. Where M of 0 is the initial mass of pollutant. Now, since the concentration T equals the mass T over V, and C of T equals C of 0 e to the minus KT, where C of O is the initial concentration. Time taken for the pollutant to reach the target concentration is C target equals C of T equals C of 0 e to the negative KT. So T is here. Now we'll say we want to reduce the level to 1/10 of the initial level. So we just plug in this value with C sub 0 equals 1/10. Then the length of time required to reach the target level of concentration is given here. Now we're going to say that the pollutant is still entering the lake. So this changes the differential equation which we established before from the start. Now if pollutant was still entering the lake, then our input-output is applied, and mass entering the lake is Q delta T, while the output is again here. The accumulation over the interval is this. Hence, change in mass during this interval is T plus delta T minus MT equals Q delta T minus R over V MT delta T. Now, if you'll notice, this term here was 0 in the previous one because we didn't have anything coming into the lake that we were subtracting from. So same again, K equals R over V. And again, when we're doing this, when we're solving it, we get the basic differential equation here with a Q term this time and K of M of T. Now we're using the integrating factor method. We can get the general solution for M of T equal here, right, equals Q over K plus C e to the minus KT, whereas always C is a constant of integration. Now rearranging with initial condition at T equals 0 to evaluate C, we get this. This is our solution. Now in the long term, the mass of the pollutant tends to Q over K. If the initial pollution in the lake was 0, then M of 0 equals 0, so we would get this as our equation here. Now mass of the pollutant increases from 0 up to the steady state, which is Q over K. Now using equation from before with M of T equals VC of T and putting K of V equals R, we get this equation here, which is the concentration. That's the first kind of big-ish of these mini lectures on mathematical modelling, and this is modelling a chemical spill into a lake with our assumptions, and then halfway through we changed some of these assumptions so that we added an extra term to our equation to account for more pollution actually entering the lake, but the other assumptions remained fixed. Please do like and subscribe. I've got plenty more to come.